Okay, so I'm going to talk about some work I've done this summer using graphical models for image annotation, and I'm going to propose some future work on those same lines, and also for a project doing joint segmentation and labeling for information retrieval. So this summer we implemented graphical models using GMTK. I have some preliminary results for HMMs. The two-dimensional HMMs are still in progress. And like I said, I'm going to propose a tree structure later on in the talk. Okay, so just a brief overview of graphical model notation. On the left side, you see an HMM like what Pavel had earlier in his talk. And instead of each state standing for a word, what we have is each state is a random variable, which takes one of several values. And then given that concept, we generate an observation. So, for example, on Pavel's model, you would have that state generating water, whereas in the graphical model, the first state becomes water, and so on. Okay, so what you see here is, for most of the rest of this talk, we're going to move up one level of abstraction. And each of these yellow circles is what one of the big circles was. So we're not going to worry about what the internal structure of each node is. We're also going to assume that the observations are always there. Because we are dealing with 24 image blocks, it's the same everywhere. So this is the model, the equivalent model to what Pavel trained. It's an HMM, but the transition probabilities are fixed between concepts. So the first model we looked at was what happens if we allow these to be trained. And then, so what we're hoping to capture here is some of the spatial information that we're clearly ignoring in using Pavel's model. In this case, we're hoping to capture the width information. And then another model we tried was a two-dimensional model where hopefully we will be able to capture both vertical and horizontal information. Unfortunately, we ran into some problems using the two-dimensional model.
Excuse me, what we had before is a scan, simply, is that right?
Yes. Yeah. The one on the left
also
is
two-dimensional, but it's a scan.
Yeah, all we have is linear information.
I mean, but we're just going like this.
Yes.
Right.
Right, so we ran into some problems with the two-dimensional model. One is, as you can see, each concept here is dependent on the concept above and to the left. So immediately your parameter space goes from v squared to at least v cubed. And this causes some data sparsity issues, some memory issues, and some time issues. For example, to train the one-dimensional HMM, we can do an iteration in about a half an hour. Using the 2D HMM, if we do an iteration a day, we're lucky. So that's somewhat problematic. Yeah, Jason?
So not the time issue, but the sparsity issue,
yeah.
You can get around by parameterizing, by decoupling the two transitions.
We haven't tried that. That is one of the things I'm going to propose to do next.
Sure.
The way we tried to get around some of the data sparsity issues in our experiment was we tied some of the parameters, something akin to Pavel's gradual training.
Which is a different idea, right?
Which is a very different idea,
yeah.
Yes. Okay, so we have these models. How are we going to train them? What we do in GMTK is we have a concept state, which generates an observation. And we have observed state, m sub t, which is always observed to be 1. And what we do is we impose a constraint from the state variable to the observation, such that this can only be 1 if the state variable is one of our annotation works, as you can see. And another approach which is similar to Pavel's forced training mode, is we want to require that every annotation is visited at least once. One of the nice things about GMTK is that
if every annotation is what?
visited at least once. So in the first model, you could have had an image where you hypothesized that everything was tiger. That would be a legitimate hypothesis. This one says you have to use tiger at least once, grass at least once, and sky at least once.
In some of the images.
No,
Some part of it.
In an image which was
this is on a per image basis.
Oh, I see. Which is annotated by this.
Right. So for each image you have some annotations, and this tells you how you're going to, the rules you're going to use to assign the annotations to the image during training. What the possible hypotheses are. Okay? So one of the nice things about GMTK is we can represent this very simply, whereas what Pavel said, it was something of a struggle in HTK.
Now there is a little problem with inaccurate annotations, right?
Right, but that's, yeah, I take the data they give me.
No, but I mean, we've discovered.
Right.
Well, you could take the annotations to be observables, which are generated from the from the true things in the image.
In other words, that
In other words, you could model the inaccuracy. You could model whether you could model whether something which takes up more space in the image is more likely to be annotated.
Yeah, but what if you have this situation, truck and a transportation vehicle? I mean, what if you have annotations which refer to the same thing?
In principle, it's possible to model anything, right? That's possible. And it's possible to do it in GMTK. It'll just probably be slow.
so if you go back to the previous slide,
I'm not saying
what you
anything
could
about
do
that.
is you could have MB1 even, like, let's say the annotation had car, you could let one car, then you could let MB1 even for vehicle, and that way you could model, you could build it in hard coded, or you could make that whole thing a distribution to be
Exactly.
estimated. That's what you're saying. Yes.
Yes.
The disadvantage of making a distribution is it drastically increases your space. There's a reason this runs fast, and the reason is it doesn't have to consider many things during training, many different alternatives.
So does this make it a lot slower? I would think so.
Yes. I will not be showing results for this particular model. It does slow things down considerably. Okay, so how are we going to do inference using these models? We want to find a conditional probability of a concept given an image. So first we're going to define the joint probability of the concept and the image, which is simply the sum over all paths that contain this concept times the probability of the path and the probability that the states in that path generate the specific observations. And then for the denominator, we simply sum over all paths instead of imposing any constraint. And then one other approach that we've also used is Viterbi decoding, where you simply replace the sum with a max. And so far, this has been actually, for most models, the best decoding approach that we have found. Okay, so how are we doing? The answer is not very well, even in comparison to how other people are doing on this task. So the top model is, in theory, the same model that Pavel has. And we're getting significantly worse results for reasons that we have not completely discovered yet. The good news is that given that we're starting from this baseline, we actually do see something of an improvement. It's a p-value of 0.051, so not quite statistically significant. So what can we conclude from this? Well, we note we need some work on 2D models. The training time is prohibitive, and as we've seen, and we don't have yet mean average precision that comes close to the other models. Okay, so what I propose is that these 2D models, I believe, still have value. We just have to find the way to train them. So one way, like Jason proposed, is to decouple, yes?
Did you try pruning?
Yes, we pruned heavily.
With what kind of pruning?
C-beam and S-beam, both.
Did you try CK beam?
CK-beam? I didn't see that option in the menu.
Which version are you using?
Uh,
No, there's a completely rewritten version.
I'm using the EM new that was in the Aurora tutorial.
Okay, and you didn't use CK beam?
I don't think so. I never heard of
Okay,
CK-beam.
yeah,
Okay.
we should talk.
Yes. Okay, right. So one approach is to try and deal with the data sparsity as well as the timing issues, is to model these as independent assumptions. And of course, you're going to have to do some renormalization using that. And that allows us to train the horizontal and vertical trains somewhat separately. So that should make life easier. And we'll look into other variations too, probably. So let me move on to my next piece of my talk, which is joint image segmentation and labeling. And the idea here is still to try and model the spatial information in an image, but we're going to go about it in a different way. So what you see here is what we've done previously. Here's a chain. Here's our one-dimensional model. We only look at each node generates an observation. So what we're going to do, the first step is we do a hierarchical bottom-up agglomerative clustering based on visual similarity. So we get a hierarchy of similarities. Next thing we do is we take a cut through the tree, a possible cut through the tree, which gives us a valid segmentation over the image. And then we label the segments. So this is the basic approach. So like I said, we're going to treat the tree construction as more or less a solved problem. We're going to take that as a given from the image processing community and focus on the cut and the labeling as the problems that we're interested in. Okay, so this is our formal model. So we're going to try and model the probability of a cut through the tree. And I'll touch briefly on some different ways we may try and model this. This is, once you have a cut for a particular leaf, what concept do you want to assign to that leaf? And then once you have the concept, you then have to generate the observations that sit under that node. So for this last one, probably our first pass model will assume that the children are generated independently, so this just turns into a product over the observations. Okay, so there are some assumptions that we probably need to make. We may assume that all cuts are equally likely. Again, in a first pass model, we probably will. And given a cut, we're going to assume that the labels are either independent or form a Markov chain in a left to right ordering. And then once we assign a label, we're going to assume that the children it generates or the observation that it generates are independent of the observations of its neighbors. We still have to work out the exact EM algorithm for this model. This was a fairly recent idea that we had, and it's not fully specified. But let me just put up some ideas that we've had so far. Like I said, for estimating the cuts, one approach would be to say, well, they're all uniform. During training, you know the number of annotations, So you can say, well, if I've got 3 annotation words, I'm not going to take a cut that gives me 2 segments on the image, because I know that this annotator thought there were at least 3 things, modulo the vehicle, car, transportation issue. Another approach is that we're going to look at the probability of view as being a composition of the probability of the number of segments produced. So maybe there are often 5 or 6 things in an image. There probably isn't one thing in an image or 24 separate things in an image. And then once we know the number of segments, we're going to hypothesize. We're going to hypothesize how those groups actually segment the image. And what saves us here is that we're constrained by the tree as to what segmentations are allowed. So we're not going to look at all possible segmentations, only those allowed by the tree. And we may try a greedy approach to eliminate the distribution overcuts altogether. So here you would just, there would be a single cut for this model, and that may or may not work. And then for the labels, so once you have a cut, you have to assign labels. You can assume that the labels are independent of each other, which is what I meant by uniform, which is similar to Pavel's training of HMMs. You could look at the number of observations that this node generates, for example. So if a node generates 18 of the 24 blocks, it could very likely be sky. It's unlikely to be a really big canoe. And another approach would be to use a co-occurrence language model where we impose this Markov. You could do this using a Markov chain, or you could do it using the 2-step approach like what Pinar talked about in her MT presentation. Once you have the labels, one approach would be to label the children independently. I've talked about that. Another approach would be to, so the problem with labeling the children independently is that when you look at this tree, if I take a node, and let's say I instead suggest that no, I want to look at the 2 children nodes, there will be no advantage in terms of generating the observations to using the parent as opposed to the 2 children, because if nothing else, I can always label the 2 children same as what the parent was, and my probability is going to be the same. So one solution to this would be to compose your observations as you go up the tree, although how exactly you do that is somewhat questionable, because maybe if you average, if you take one feature vector over the entire image, all images might look pretty similar to each other. So this is still a step that needs a lot of work. And the other thing is, if you take sky and you take building, you might get zebra out, something that looks like a zebra. And you really don't want that for image annotation. So to evaluate this, what we're going to do is we're going to initially stick to the Corel data until we at least get our mean average precision up to the level that other models are working at. And we're going to use mean average precision as our criteria. And then hopefully at some point we'll move on to the track annotation task. And I'll take questions if anyone has them. Okay. Oh, I'm sorry.
So this notion of sticking with the Corel database, I think is a little bit risky. It almost seems to me that your models are going to require a lot more data than the other models that we've seen here. And it does seem to me developing methods for found data or something like that that can allow you to actually do a little bit more might actually be a wise thing to do. Ignoring the trick to work on a small data set, you may never get good enough results because you may not have enough training data. It does seem risky.
That's a fair. I'll admit I haven't considered that, but the advantage of Corel is that we have it. It's here. We can do work on it. Developing a system to go out and find this data, like you talked about using found data, may take, I mean, that's not a trivial issue to solve, I don't think.
But I do, so if you were trying to get images, you could actually go out and look at captioned images from newspapers or something like that. That may actually be a better thing to do.
That's true.
Actually, no.
No?
Because the captions are very different kinds of things.
Sure.
I say Alan Greenspan and then talk about the economy and the finance, which have nothing to do with the picture.
Right. So,
Well, that's
economy's not
pretty
here,
risky.
right, Connor?
Pardon?
yes.
So you're getting your tree from using image growing algorithms and sticking similar regions together. Is that right?
Yes.
So should the similarity of adjacent regions in that algorithm affect where you'd like to cut?
Possibly. I think.
So the segmentation will be done once, basically, and then you're going to assume that...
No, we're going to hypothesize all cuts.
Right, but
But there's only one tree.
There's one tree.
there's one tree. So would it be possible to basically, once you have your trees for all the images, to then compile the problem into a graphical model, so you don't have to worry about working out the answer?
I haven't thought about that. There's some, I think you may run into difficulty because from what I've understand, and I've only been working with GMTK for 6 weeks, so please correct me if I'm wrong. GMTK does not deal tremendously well with when you have a changing number of things. So if I knew that I was always going to have a segment generating 3 observations, it could handle that well. Saying a segment is going to generate 1, 2, 3, 4, up to 24 observations becomes somewhat more problematic, I think. But like I said, I haven't thought through turning this into a graphical model problem enough to give you a good answer to your question. Yeah.
So the segmentations are still based on these squares? So you're breaking the images up into squares, or actually doing object-based segmentation?
Most likely not object-based segmentation.
Because, well, first of all, there's a lot of work in the image processing community to try to do object-based segmentation based not on sort of a fixed cut of the region into non-overlapping squares, but to actually try to look for texture and color and illuminance and all these different features that try to produce an image that's segmented more accordingly. And secondly, the reason why I ask is because right now, if you do this square-based image segmentation, potentially, and then the underlying structuring is based on a tree, there could be regions that really naturally should go into multiple clusters, and they're not going to get into a cluster until you get very high into the tree. So, which might be a problem. Like if you have one of those squares which is equally tiger, equally water, and equally, grass, then where is that going to go? I mean, and probably there will be quite a few of those because you're segmenting regions
Jeff,
arbitrarily.
remember the static image that he had segmented? That's what the segmentations usually look like in terms of image segmentation. So they don't actually tend to correspond to specific things most of the time.
Not specific things, but specific subsets of things.
Pretty noisy.
Well, actually,
Let me quickly address your first question. The reason I would say that the first pass would be using blocks is simply because we have tried using image segmentations. Pinar has tried it. We tried it briefly early on in the workshop. And one of the things that held for all models, any variation you wanted to try, was that the blocks worked better than the blobs that we could calculate from the image.
The reason is that segmentation is not usually giving the best results. Again, there are very errorful segmentations. So errorful blocks is better than errorful segments.
but you're clustering anyway, right? So what if you did something like you segmented based on color, then segmented it based on texture, and then
This
segmented
point's
it based on structure. And maybe there's some other features, and then you intersect all these segmentations, and then you start clustering things together, and you get these very non-convex, you get clusters which correspond to very non-convex regions, arbitrary, based on the intersection of all these segmentations. And that would be an approach. And since you're doing clustering anyway, that would be. So would that be a reasonable thing to do?
It very likely could be. Another approach similar to what you mentioned would be you build one tree based on color, you build another one based on texture, build another one based on some other ones. You have a distribution across those trees, you guess a tree, and then do the rest of the algorithm. So now you have a few trees per image. I'm getting the feeling that Sanjeev wants me to stop.
Yeah, we are now 35 minutes behind. If we go on this way, we'll go past 12. So we should stop and continue with the next speaker. So further discussion if we have time.
Sorry. Hi, so I'm Matt Krause, and I'm going to talk about predicting visual concepts from text. It's sort of the inverse of the previous talks, where you're going from a picture to words. We're trying to take some words and predict what ought to be in the picture. So, in terms of our overall outline, we move to that green block down there, and we're here. So, to give you sort of a flavor for what we're trying to do, here's a little example. Imagine you worked at, say, a news network, and you had some message you wanted to illustrate. So, like a piece of a piece of audio, or maybe some text. So, for example, here's a piece of audio.
It's much the same in this summertime glacier avalanche, with relaxed tourists expressing surprise as it begins. Seconds later, they are swept away. Miraculously, all survived.
So you want to figure out what sort of pictures should accompany that text. And if you want a little more help, here's the output of a speech recognizer going over the beginning. So, anyone want to guess? Come on.
Ice cubes. Ice cubes.
Anybody else?
Summertime.
Yes? Okay. So here's actually the image. Or the movie. No, that's not it.
Or run away. It's much the same in this summertime glacier avalanche, with relaxed tourists expressing surprise as it begins. Seconds later, they are swept away. Miraculously, all survived.
Whoops.
So that's sort of what we're trying to do. We want to take...
Because it's too dangerous to send to film crews.
Yes. So we want to take the stock footage, put it together. So yeah, so that's our goal. We want to take the audio and figure out what ought to be in the picture. So for that...
So you're going to synthesize a picture?
No, we're just going to predict...
Looking for something.
We're going to predict what ought to be in the picture.
Yeah, Michael, if
So-
you're successful, we can synthesize.
That's the
Yeah.
next.
Yes, then we'll fake the news. No. Okay, so... Yeah, so given sort of that audio...
Excuse me, what was done here?
Well, let me tell you. So given that audio, we want to predict that there ought to be water, tourists, it should be outside, there should be ice because it has a glacier, and perhaps that there are tourists who are now swimming. So formally, we're going to do this way. We're going to assume there's a hidden variable which generates query words from a document image. So we introduce the hidden variable here as C, and then if we assume it covers the whole sort of transition completely, we can split it up into two terms, like this, by summing over all C's. And so I'm going to talk about this component here. So here's another piece of ASR, which is a little bit less exciting. And to do this, so we start with this. And so it says, Steve Fawcett in his balloon, solo spirit.
Well, why are you doing this from the ASR output?
It's news video, so we don't have the text.
So you're going to generate stuff from the noisy ASR output?
Yeah.
So imagine you're watching TV with your eyes closed, and you want to, or your back's turned, and you want to figure out what's on the screen.
Plugs in your...
And a little bee buzzing around.
Pretty much, yeah.
Trying to carry a conversation on with you at the same time.
So here's a piece of recognizer output, which is admittedly noisy. This is actually is tonight, and yeah.
And Caucasus is probably...
No, Caucasus is right. The mountains.
Well, it's not spelled.
Well, it's a different kind of US.
Yeah. Well,
Arsenite.
I mean, it doesn't know that. So we have this, and we need to extract features from it. So we built this pipeline. So we start because ASR is unpunctuated. We need to insert sentence boundaries, and so we do this with a pretty simple.
Again, just that, why are you tackling such a difficult
Well, why not just start with like the correct text and see if
As you see, it's really not that
Because
bad.
we have annotations available for, with ASR and the shots. So that's.
I should sort of point out that, yeah, it's a component of this system. So, I mean, if we use correct text, there's really not a lot of value. So yeah, so we built this pipeline to extract the features from it. So we start by inserting sentence boundaries, and we use a really simple heuristic. The speech recognizer outputs sort of speech segments for one individual speaker, and so we find the longest pause in there, insert a period, that cuts it in half, or into 2 pieces, and we recursively do that until we hit some minimum length, or there's not a sufficiently long pause. Then we use a big language model to restore the case to the text, and that uses, a large language model which knows which words are uppercased and which aren't, and some simple rules like things after periods should be punctuated. So now we've got something which sort of looks like text. We run a named entity detector over it. And so that finds names of people, places, locations, and it's even slightly more fine-grained, so we can tell what gender a person is from their name usually. At the same time, we part of speech tag our text and pull out the nouns.
So, again, just another stupid question. Why not just look for all the named entities and nouns and then just populate things with one vis term per named entity or noun? Why isn't that a reasonable thing to do here?
Well, 2 things. We're not predicting vis terms. We're predicting sort of the concepts. So yeah,
Or concept,
so you predict face.
whatever.
But we want to do it for other concepts too. So I mean, just getting people's really not that interesting.
Well, any noun you manage to locate.
But even nouns can show up in like a variety of distributions.
I
Right?
guess I'm just curious, if you do are you going to have something that says that you can do something better than that rather trivial model?
We should probably,
Just on.
Yeah, look, I'll show you the end. It's really not that bad. So we have a list of nouns, and we run through WordNet to throw out abstract nouns, because as you pointed out, like things like warmth are really well, maybe warmth, but like happiness is not really going to have a defined visual correlate. So we kick those out. But it's not.
Snoopy, I don't know.
Fair
Happiness
enough.
is a warm picture.
Okay.
okay.
So then, at the same time, we can sort of, because WordNet's a hierarchy, we can walk the hierarchy and figure out if several of our terms fall under one group. So, so we've combined this, the concrete nouns, and the WordNet concept into our feature set. So here's sort of a little example. We start with this piece of ASR text, again about him and his balloon floating around. And so we insert the periods, and as you'll notice, it does reasonably well. They tend to fall on clause boundaries instead of on sentence boundaries. So it wouldn't make your English teacher proud, but it works. So then we run case restoration on it, and it turns into something semi-reasonable. So now we can use sort of standard text processing techniques. So we run a named entity detector over it, and it finds 2 proper names, Steve Fawcett and Black Sea.
So this
is actual data.
Grozny.
So it misses Grozny, and Chechen is sort of, and Caucasus. Then we part a speech tag, and these are the things which it thinks are nouns. Most of them are, towards is not. So using the WordNet thing, WordNet walking, it actually pulls out towards and tomorrow because it doesn't have them listed anywhere in the noun hierarchy. So we end up with this list of nouns here, and we find that a number of these words fall under the nature heading, probably daylight, coast, maybe Grozny. So that's our feature set. We turn it into a bunch of binary bit vectors for the machines, but that's what it semantically looks like. Huge. We have a large vocabulary of nouns and named entities, about 6,000 total, and we use a 3-shot context to classify. So we look to classify the current picture. We use the ASR associated with that, the previous shot, and the next shot. So 6,000 times 3 is very, very big. And we want to use a subset of this for sort of 2 reasons. One is just sort of pragmatic, that we'd like to go home at some point. So smaller feature sets, train faster, use less memory. And sort of on the more performance-oriented side, if we get rid of distracting features, we might expect our performance to go up. So we have 2 strategies for feature selection. For the first, we just throw out rare words. If a word only occurs once, it really doesn't have a distribution over concepts, it's in one concept. And even twice, the distribution is sort of shaky. So by throwing out everything which occurs less than 3 times, we cut our feature space more than in half, from 18,000 to a little bit under 8. So now we're left with a reasonable sized feature set. But we want to throw out the low value features. We do this using a technique for machine learning called information gain. And it just measures the change in entropy, given that you know the value of a single feature. So if you know that, say, a male proper name is present in the shot, how does that change your knowledge of the class distribution? So we compute this for each feature, and this gives us a rank list of features. And so in sort of the binary case, we try to decide if one concept is present or absent. We end up with a rank list that looks like this. So these are sort of interesting. For basketball, you get basketball words. You get names of cities, so where teams are based. You might like Chicago Bulls, Washington Wizards, stuff like that. And you get basketball-associated words. Game, point, basketball, title, win. And as you go actually further down the list, you start to get names of schools and other things like that. For Sky, on the other hand, there's sort of not a coherent theme. I'm not really sure what juries or research and fiber have to do with skies. It's possible that these are negative predictors, so they suggest that sky is not present. But again, you can't really tell from the way the information gets computed. So we use that to figure out how many attributes we should keep. So I ran one of our classifiers and counted up the number of attributes. So I ran one with 250, 500, blah, 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 out to here. And you notice that after about 2,500 attributes, there's really no gain, or features, there's really no gain. And so this is good for us because it means we can make fairly compact models which train quickly. And so that's what we did. We tried training a variety of classifiers. You see them here. I'm only going to talk about the ones in black because the ones in gray didn't work. So naive Bayes is sort of the great granddaddy of all machine learning techniques, I think. And here's the obligatory formula. And so we built 70, yeah?
Just again, clarification. These are visual concepts or these are just concepts?
So it's the same vocabulary.
Yeah.
The concepts are the annotations of the image.
The annotations of the image, which may not have anything to do with the visual content. Is that correct, or?
No, the annotations of the image are supposed to...
These are the static images?
Yes.
This is the Corel data
No,
set.
Trek.
It's not,
Trek.
It's Trek, but Trek is also annotated based on the audio content. Is that not
No,
true?
we restricted only the 75 concepts that we chose here were restricted to the visual concepts. So it's the same task. In some sense, it's the same task as the previous three talks that we have heard, except that we are modeling the same concept, but the features that we are extracting are from the words.
Mm-hmm.
So in what all the three people previously talked about, their models were looking at the image and trying to figure out which one of these 75 things or more might be in the image. Now Matt and Dietrich and Giri are looking at the text that goes with that image and trying to figure out what might.
Okay.
In a sense, it's image.
But again, and you've restricted yourself, so you're trying to predict literally visual concepts,
Yeah,
not
make it
verbal
comparable.
concepts.
Yes.
Illustrated, the most frequent concepts are things like text overlay, non-studio setting, face. Those are the things to be predicted.
So in a sense, this is image annotation sort of blind. So you take the text and you try to predict what ought to be in the image. Okay, so yeah, there are binary classifiers for each of our concepts, saying whether or not they're present or absent. So we estimate with, Bayes' rule. DW is counts of the features from our feature set, and C is the concepts, which are the annotations on the corresponding images. So sort of a three-way hop. The annotations for the images, and we take the features from the associated ACR, or ASR. We build the classifier for support vector machines the same way. Well, it learns differently, but they're binary, they're 75, and they use binary features. We also tried a language modeling approach, and that's conceptually similar to naive Bayes, except it's multinomial, so we use counts instead of binary presence or absence distinctions, and the distributions are smoothed. And we also did feature selection slightly differently, and it is just, we pick the number which works best on a held out test set. There's no sort of ranking, it just goes from there. But other than that, it's the same. There's a language model for each concept. You take a piece of your test data, and you find the model which minimizes perplexity on that concept, or for that piece of data. MaxN is slightly different. It uses the binary constraints like the support vector machines in naive Bayes, but there's a single 75 concept model, and so we find the likelihood of...
Okay.
Sorry?
Actually, how does this differ from stuff you've done already?
How does it differ from what stuff?
In terms of predicting concepts from...
From the text?
Yes.
Oh, the stuff that we tried back at IBM was a very simple. We just ran it as a no copy retrieval system.
Just
no copy.
Okay.
So we just run. What we do is we get shots,
Mm-hmm.
and for we know what their annotations are, and we do some simple counts. Say these are the top 50 words, and we manually prove that list by looking at outdoors needs farms, clouds, and so forth. Run a simple copy retrieval, and it gets it back.
So these are just more sophisticated.
Much more sophisticated process. Yeah.
And so you get a rank list. So here are our results. We are surprisingly not bad. So here's chance performance in yellow, and here are our three sort of best performing models. you'll notice that they're all much larger than yellow, particularly the language model, which is in gray. Our results on sort of less common concepts are pretty interesting. So basketball and weather were way, way, way better than chance. And we think this is because there's a distinct lexicon for basketball and weather. So Peter Jennings doesn't slam dunk during the nightly news, and cold fronts only show up in weather news. So there's a distinct lexicon for those. But what's encouraging is that we're also better than chance on a number of concepts that don't seem to have their own separate lexicons, like indoors and sky. Like, so on the newscast, they don't really make a big deal of the sky being present behind them. And similarly, they're not, oh, we're inside. So this is encouraging, and here's sort of our mean average precision for 3 of our systems versus chance, and you'll notice that they're roughly comparable to the vision systems.
Chance is so hard, it is so good because you're also ruling out the negative examples.
Chance is good because the concept distribution is really weird. So faces occur in, I think, about 50% of the stuff. Similarly, text overlays are in more than half the shots. Other concepts occur in 0.0005%, so it's, I think, just sort of trading on that frequency. But we're much better than it. The language model's mean average precision is 0.125, which is sort of competitive with the vision stuff, which is good, particularly because we're not actually using any vision stuff. So we did this all in a retrieval context, and we're wondering if this will be helpful for
You
retrieval.
didn't compare this to the Okapi measure.
It's the vocabulary is not comparable. The minor differences that we need to clean up, but we haven't done that yet.
Were some of your shots 3 seconds long here, or did you restrict the shots to be down like at least one word?
No, we used everything. As you'll notice,
We have empty as a predictor, right?
here, empty is either a very good or a very bad predictor for basketball. And so yeah, there are actually a lot of shots where there's only a few words, or no words at all if the shot detector was tricked.
I'm sorry, what does empty mean?
Empty means there were no words in the shot.
Oh, I see, and what's previous mean?
So we use a 3-shot context.
Pardon me?
We use a 3-shot context when we classify. So to classify a shot, we look at the previous shot and the next shot.
So game previous means that the previous shot contained a game.
Yes. So you could imagine that it might be something like, now we go live to the next game, and then they cut to the next game.
But some of the shots are as long as 3 or 4 minutes, like in C-SPAN, is that what I remember hearing?
Yes.
So and you just use all the text?
We didn't carefully say that I'm going to have only a story boundary or something like that, or a fixed length window. None of that was done.
We did add in the length of the text as a feature, and that got us slight performance gains.
What is the ordering here? It's from the most frequent thing that's present?
No, this is ranked on information gain. Information gain? So this is the best predictor for basketball.
Empty.
Yes, so nothing. So either the speech recognizer didn't pick up anything, or there actually was nothing. So maybe music or something like that.
And then it says Chicago, and that's the second.
That's the second best predictor, is the name of the city, and so on.
Matt, you should go on.
Yeah. So we want to know if this will help for retrieval. So we did a little experiment. Here are, we took the Trek queries, and 4 of us independently predicted what we thought should be in the picture.
What
concepts should be in the picture from our restricted vocabulary. So for example, for shots of a person diving into some water, you want a person, some water. For shots of the White House, you want a building. It should be an outdoor shot, so outdoors. It might have sky, water from the fountain, so on. And so here's our performance on concepts which are relevant to retrieval. So outdoors occurred in 68% of our annotations on the queries. And our average precision is 0.434, but chance is only 0.270. So that's good. And then our average precision is much higher than chance on almost all of them, and I think it's higher than chance on everyone. Yeah. So that suggests that this should be useful for retrieval. So in summary, we predicted visual concepts from the speech recognizer output. We tried a variety of classifiers and got fairly decent results. And we expect to see performance in retrieval when we integrate this into our entire system. So any questions?
Yeah, can you go back to the previous slide? Maybe the one before. So I'm confused. So you have the query, find shots of a person diving into water. You throw out that query, you say replace it with these concepts. And then you look at, and then you're giving the average precision for, did you find persons diving into water? Is that,
No, just, yeah.
So if you have a picture, so imagine that you want to find a picture in response to this query. What do you want in that picture? You want a person. You want water. They should probably not be in the studio. And so we sat down and four of us independently made a list like that. We had very high agreement. It was almost 100%, except for sort of things like, oh, that's in the vocabulary.
Using the 35%.
75.
Using the 75 concept.
When you did it manually, this is just to avoid the problem of, you're just avoiding the problem for the moment of dealing with automatically generating that list from the text, right?
So this is sort of like an Oracle experiment. Like, we know this is reasonable because we came up with it.
So then what did you measure with the average precision? Is the part
To see how well do the classifiers do on the concepts that we picked were relevant for the query.
So there are 10,000 shots on which concepts have been annotated. And what he shows you next is the performance of the classifier on that set for these concepts.
For the
But
concepts that are
not
most-
relevant to the query. This is,
That- these are
average
the query
precision is
relevant.
not relevant to the query.
No, the average precision is not on the query. It's on the concepts which are related to the query.
So it's the average precision of that concept, and importance tells you how important it is for the query.
So for example, one of our concepts was beach, and that didn't show up in any of the queries, and we think it's probably a little bit unlikely. So
And how did you get importance for a query?
it's just a percent. So this is in 68% of our annotations. This
Of
is
the
in
human
48.
with the experiment that we did.
Of the 25 queries, 68% would require
An outdoor
detecting
shot.
outdoors.
Okay.
So about half would require a person, 40% would require sky.
It's just the statistics on a particular set of queries,
Yeah.
Yeah, if we had more queries, we could estimate something like this mapping automatically. But from 25, anything we do is going to be, yeah.
Let me just go back again.
Uh,
The column importance says what's the percentage of shots which are annotated by the word outdoors?
No.
No.
Of the 25 missed queries,
Missed.
National Institute,
Oh, NIST, I'm
Yes.
sorry.
of the 25 Trek queries
Yes.
of Trek 2003, this percentage would require a shot which has outdoors, according to 4 people in this group.
According to their annotation. In other words, they took the sentence which said fine, blah, blah, blah. They thought that a proper response to it would have these
Yes.
things annotated.
Exactly.
Yes.
And now,
And so the point is that we can do well on those concepts.
We should, yeah,
Okay,
we should
so-
go to your proposal.
Any more questions? So,
No, no more questions. You go on to
okay,
your
good.
proposal.
So while we were doing this, we found out that we noticed that there's one more source of text in video, which we really hadn't been exploiting at all, which brings me to my proposal for joint visual text modeling for OCR. And so there's a lot of motivations for wanting to do video OCR, but in a Trek context, part of the NIST sort of information requirements are that you should be able to find specific persons, places, events, and locations. And these are exactly the things which have text overlays in broadcast news. So for example, one Trek query is find me shots of Congressman Mark Souter, and so there he is. And in fact, there's his name in both images. And in fact, in the Trek corpus, every shot of him has his name in the picture.
We'll also have to see a lot of shots of live, I guess.
Yeah.
If you look for Mr. Live, you're done.
So here's another Trek query where you're asked to find shots of containing information about the Dow Jones Industrial Average. And it actually asks explicitly for text overlays. And so if you could read those, you'd be ahead of the game as well. And so here's one final one. You're asked to find shots of the Tomb of the Unknown Soldier. And if you could read that inscription, you would know that it's the Tomb of the Unknown Soldier. So this brings me to a really important point. There's sort of two kinds of text in videos. There's scene text, which is sort of captured with the camera. And then there's text like this, which is inserted in the studio. I'm only going after this kind because this is really, really hard. So even with scene text, even without scene text, there's still a lot of work to be done. Here's the output of a pretty well-known recognizer on this. And so, yeah. Yes?
And of course, there's the other problem with something like CNN headline news, where you have the news feed that has nothing to do with the image that's being presented. It's just up.
Well, there's two really simple solutions to that. One, it's moving, and the other captions aren't. So if you just look at difference, or if you want to be even less principled, it's at the bottom of the screen, just cut it off.
You could sell that by itself.
Yeah. File that patent now.
So yeah, So there's a lot of work to be done on video recognition. And this is partly because the video images are much lower resolution than sort of scan printed OCR, which is pretty well mature. And also because the background on sort of text OCR is plain white, where this is sort of excitingly ABC colored and has that gradient. So the goal of my project is to improve video OCR accuracy by exploiting other information in the audio and visual streams during the recognition time. So one sort of counter-proposal to this is why not just use that information directly? And so here I have another example. Imagine you want to find shots of Pierre Thomas. So you take the text and you find every instance of his name, and perhaps you throw out shots that don't contain a face. And then you pull those back as your retrieved set. So if you did that, the picture corresponding with this shot is that, which is not Pierre Thomas. This is Pierre Thomas. And if you could read the name, you'd be in good shape. But if you just went on the ASR accompanying with this shot, you'd miss it completely because he doesn't say his name. He says someone else's name who occurs further down in the broadcast. So the problem just sort of keeps compounding. So text overlays provide really high precision information about query relevant concepts in the current image. So the things you want to query on is in the current image, so you really want to go after it. And if you had good video OCR, you can. So in order to find it, in order to recognize the text, you first have to find it, and I'm actually going to take a pass on that. IBM has a number of tools for finding text overlays, and CMU has the text boxes in their check feature set, which they made public. So I'm just going to use something like that.
So how accurate is typically the level of locating the text boxes?
It's a fairly, it's a reasonable, there's a lot of work, even before I joined IBM, which was doing pretty well. We used that for one of the track exercises. It was the best detector in, I think, 2001.
So you get it about half the time, a quarter of the time?
Much higher.
Yeah, it's
90%.
It's in the 70s.
70, 80%.
70.
So it's sort of like the ASR problem where it's going to be noisy, but it's still workable. So I'm going to do a little bit of image processing, normalize the text regions to constant heights, which is just scaling, perhaps a little bit of image cleaning if it needs it, and feature extraction. I'm going to start by looking at color, features, and edge strength and orientation, because those seem like they should be really well-defined for text. Though as part of my project, I'd like to look at other sort of visual features and see what they can tell me. So I'm going to use those features to build an HMM-based recognizer. It's a left-to-right recognizer, almost exactly the same as one from speech. And in fact, people at BBN actually built an OCR system for printed text by just replacing the front end of their speech recognizer with a pixel detector, and they got reasonable results. So this is a left-to-right HMM. Here's the sort of Bayesian network view of it, where each part depends on a picture, and it's a trigram model, although I also want to look at other order ends. But that's pretty simple. And in principle, I could also take away the image features, replace them with the output from someone else's recognizer, and use this as sort of a cleaner. And so improved features should get me some gain, but I think the big gain will come from better language modeling. So I have sort of an interesting idea I want to try with language modeling. I'm going to start with a background language model based on some large held-out corpus, and interpolate that with a cache from the words surrounding the shot where the text overlay occurs. So I might take maybe 30 seconds in each direction. And so the theory is that things which are said in the ASR correspond to things which will either sooner or later appear on the screen. Furthermore, I might do a little bit more processing on the cache and pull out interesting words. So named entities often occur in the caption bar.
Do you have all the text in the OCR, whatever the text in the boxes? Do you have a set of training data there?
I made one.
You made one.
So I started building one this summer, and I have about, say, almost 1,000 examples. And it's easy to do really quickly because you just look and type, and most of the time it's 2 or 3 words. So you can do several a minute, and it would not take long to build up.
And you didn't try and build a language model off of that data for this?
That was
in the context of
that was an early idea, but it sort of got pushed back by the classification, which worked pretty well. And so yeah, but it's easy to collect that sort of training data, and maybe an afternoon spent would be fun. So anyway, yeah. So I have 3 language models, and you can somehow interpolate them. Here's a log linear model, but ways of combining them are reasonable as well.
Is there an assumption for names in vocabulary you recognize?
Yeah. But actually, on the Trek data, most of the names are recognized properly. So I don't know if that's because it was tuned for broadcast news around that time period. You're nodding yes, so yeah, but that is a sort of reasonable constraint.
And you can also always throw in a sort of a phone book.
Yeah, we can throw in either like a phone book or gazetteer somewhere in here. So evaluation is pretty simple. I can use the TrekVid data, character error rate to compare the performance of my OCR system versus my manual transcriptions. And then mean average precision, I can drop into sort of a retrieval context and see if it helps for an overall system. I've heard that that's been done before and it's worked well, so hopefully with better video OCR, it worked better, and we have relevance judgments for that. So in summary, information from text overlays appears to be useful for video retrieval. The general character recognition problem is really hard, but by constraining it to overlays and by throwing in external knowledge sources, I think we should be able to improve accuracy. So here's sort of the summary of the work plan. Pass on this, select features and extract them, do some height normalization, build an HMM recognizer. It's the same as speech, so we can use almost everything which has been figured out over the past 30 years, and then add in a language model.
So it seems like the comparison condition would be to do a sort of a standard pipeline where you do mathematical morphology to get the best possible characters, rescale them, pass them off to an existing OCR system, which I understand is typically done.
That's how it's
So you
generally
have
done.
baseline numbers on that that give you an idea that you can do much better here? But because you're going to put a lot of work into the character processing side of this that will duplicate effort that others have done already.
Yeah, again, there's nothing in this model that prevents them from not using that information. In fact, one of the models that we showed can take the video OCR output that someone else has already done, so it can exploit all the morphology that's, you can run a commercial OCR system, and still the HMM will work on top of that as a channel model to clean it up. And then the main interesting point is the language model, which is exploiting the ASR associated information to clean it up further.
Commercial OCR systems don't use any sort of LM.
No. They have their own LM.
But it's not cache-based.
Well, they do diagrams and diagrams.
Yeah.
Letter diagram.
Yeah, letter, but not
Yeah,
language.
so there is no gazetteer in them to say this.
I mean, it would seem
No,
the
they
biggest
have
problem
problems
with the commercial OCR systems is they're not trained on this type of
Yes,
data,
yeah.
right? So any form of adaptation is going to help.
Right, and that's exactly what I was sort of planning on doing. So
The other problem is the background is, removing the background is a really hard problem, and that's where most people have trouble.
So yeah, if I go with sort of a commercial OCR system, it's already pretty much got this built in, although I could add in like a gazetteer, so then I just use these two components. Yes?
So why, two questions actually. Why, number one, concentrate only on text overlays? And number two, if you're concentrating over on text overlays, what do you do about false positives? Because there are going to be plenty of vertical, sort of well-situated and clear pieces of text that are not text overlays. For example, when there's images of storefronts and images of things that generally have clear text on them.
So I'm not gonna, I guess I sort of phrased this wrong. If I could get a scene text, I mean, that would be fine, right? If it trips the text overlay detector and then gets sent further downstream, then we'll try and process it. But if it's something like this, I actually cleaned up so you could see it from the back of the room. Like in the actual Trek image, there's almost nothing there.
So an OCR on this will just stay up?
Yes. At least I would be willing to bet it would
I mean, but the
choke.
other thing you could do is you might strip out text that's been rotated or a little bit, or it's sort of moving around like this. All of the text overlays are going to be stationary and are going to be well situated in the image, well centered and all this kind of stuff.
Yeah, the ticker.
So will you be filtering stuff that's not looking like that?
I think many of the overlay detectors do that already. So they look for a stationary image. So if if the pixel only moves maybe 1 or 2 pixels per frame, then it's not going to be moving. But if it's moving, then it just sort of gets ignored.
So let's stop here.
So Dietrich is not going to talk about the retrieval results.
Okay. So during the past 3 hours, you have seen first kind of how the problem was taken apart into several sub-problems. And the goal of this talk is now to put everything together again, to do experiments and also to provide a summary. So you're in that part. So we started out somewhere here. That is, we have an information retrieval problem. Our query is made out of words and with terms, and also our documents are made out of words and with terms. And we picked a language model-based information retrieval approach. That means that we have to estimate that probability. And to make the problem simpler, we decomposed the matrix into 4 submatrices. That's the standard text retrieval part, and those were the 2 parts that we worked on. We had here machine translation, the relevance model, and the hidden Markov model in extracting concepts from images. And that block is extracting concepts from the ASR. Now we have to put all the components together to get the probability that we want. So that's retrieval model number 1, that we make the assumption that the query words and the query with terms are independent. And let's focus on the part that's coming from the query words. Here we do a linear interpolation of a standard retrieval model and the model that relates the query with term, the document with terms, to the query words. And of course you can do the same thing with the second component of the model, and then you'll arrive at something like that. And all 4 parts of the matrix have been taken into account, and there are 2 free parameters that have to be adjusted. But so far we got only minor improvements from that approach. Retrieval model number 2.
Sorry, what is your baseline now?
Baseline comes later on. So this is just a kind of a comment that after it didn't improve a lot, we just didn't consider it any further.
It's the text-only
The text
system.
part, text-only system is the
Sorry.
Not numbers, but conceptually, the baseline is just...
The baseline is that block. It's a standard spoken document retrieval as done in track for the, I don't know, past, I think they stopped in 2000 or something like, yeah, but it was done several years in track. Okay. So, we start all over again. That's the probability that we're interested in. And the models that we have are of that structure. A probability for the query word, for example, given and the document with term. And we can obtain that probability from the one that we are actually after by just calculating it as a marginal. That's just the marginal of the other one. And we can do the same thing for all 4 matrices that we have. They just marginals to the distribution that we are after. And that's precisely the setting of a maximum entropy problem. And usually people do it numerically and get some results. We picked something different. We just did the iteration by hand, just the first one that's still doable. And when you do 1 iteration by hand, you'll arrive at that formula. So that's now a linear combination of the logarithms of the probabilities. It's kind of a log linear interpolation. Okay, now we are coming to the actual experiment. Up here we have our standard spoken document retrieval system. And that's the retrieval mean average precision that we get for this, 0.131. And now we throw in 1 more component. That's the component that extracts concepts from the images. Just a reminder, for the task we had 3 approaches: the machine translation approach, the relevance models, and the hidden Markov models. And the concept annotation, mean average precision, were those figures here. You see that they are relatively close together. Relevance models gave the best concept annotation performance. But when we now look at the retrieval performance, then it turns out, and that was a problem, that's an issue that was already addressed in the beginning by somebody in the audience, concept annotation performance not necessarily has to translate into retrieval performance. And it turned out that actually the machine translation approach gave, right from the very beginning, a good retrieval performance. When we tweaked the HMM, we could get up to the same performance, but with the relevance model it was a little bit tricky. So we picked the machine translation approach here, And now we got an improved retrieval performance of 0.139.
What does it mean to say that 0.13 is bigger than 0.13?
Pardon?
In what sense is this improved? Is it?
It's
a larger number.
It's a large number, yes.
No, did you do
And we can come to significance of all that later on. So, and also to kind of we can of course do all combinations of two blocks, and we are behind schedule anyway. So we'll just throw in the third component. That is the model that extracts the concepts out of the ASR, the same 75 concepts. And just as a reminder, here we had a mean average precision of 0.125, which is comparable to the machine translation performance. And that actually had the images. Okay. And now the retrieval performance goes up to 0.149. And to answer your question, that improvement of the baseline is statistically significant. And that's, to our knowledge, the best result given in the literature. There's only one publication, and they're marginally better than us.
Wait a minute, 0.162 is called marginally better than...
It's again...
0.149 is called substantially better.
No. If you look, this is statistically significant, this difference. We can't do a test here, but if you look at kind of, we got more than half the way to that result.
And why is that good? I'm sorry.
So
why don't
what were they doing to get the
They were using that matrix as well, and neither this nor that. We tried that as well, but it didn't work for us. So
they know something you don't know.
yes, and they didn't tell us. So they published. You know, it's like these.
This is automatic.
And yeah, but
Yeah, okay.
Could you throw in their model for the lower right button?
I mean, it's like these broadcast news have 4 DARPA evaluations. You would never go to Cambridge and ask them, give us all your components for your rich transcription system and we'll throw it in. I mean,
Well, you can ask them to run it on data.
yeah. So, of course, could try to do something like that, but a little bit skeptical whether you'll get anything else from them.
Who are they?
Group in Amsterdam, are in de Vries. Okay, that's the recall precision graph. And you see that in the region up here, you'll get a consistent improvement over the baseline. Okay, summary. What were the difficulties that we faced during the past 6 weeks? We had to cope with the inconsistent annotations. That was already quite a topic during this presentation here. In the Corel data, sky was sometimes not annotated. The annotations in the track data are sometimes very abstract and don't really relate to objects in the picture. Also, this issue was already discussed. We just used kind of the standard color, texture, and edge features on the keyframes. And of course, we would like to have, or would like to have played around with the features as well. But given it's just 6 weeks, it's clearly outside the scope of such an activity. And it would have distracted us from the overall task. The same thing holds true for the segmentation. So we had a square segmentation of the images into 35 blocks on track. And yeah, that's probably not the optimal thing, but there was no time really to play around with that. And finally, for the task extracting the concepts from the output of the speech recognizer, it seems to be a pretty hard task, and it would have helped if you had some idea of how far you can really get on that task. And those limitations directly lead to kind of potential future work. So with respect to the incomplete labelings, let me just briefly go over this. There was a proposal by Desislaver. Then we have this bottleneck of the 75 concepts, and it would be nice to go beyond a set of 75 concepts. That would require larger training data. That would be one approach, or direct modeling. But then you would run into problems of data sparsity. And so we did some preliminary experiment in that direction, so you would really have to cope with data sparsity here. Then the modeling of spatial and temporal dependencies. Actually, Charlai's proposal was with respect to the temporal dependencies, and Brock's proposal with respect to the spatial dependencies. And then query-dependent processing very often helps in information retrieval. For example, if you are looking for pictures of, whom did we have? I don't know, Yasser Arafat or so, then you may want to use your OCR features that you extracted, and that relates to Matt's proposal. So, summary, we extracted concepts from images by using the machine translation approach, and kind of the punchline here is that the simple cross-lingual information retrieval worked surprisingly well, and we didn't get anything out of things like IBM Model 4. The relevance models gave the best numbers for concept annotation from images. The hidden Markov model approach for concept annotation was a newcomer here. Kind of, they just started during the workshop working on that, and they got, within that short time, and in particular during the last 5 days, extremely competitive to the other two approaches. Yeah, punchline for extracting visual concepts from speech recognizer output. We were really surprised that we could actually find people in the avalanche example just by listening to it. So, and the results are comparable to the machine translation approach. For the fusion, adding multiple sources really helped, and in particular, the log linear interpolation is a method to use for combination. And finally, we got a 14% relative improvement over the baseline, which is a statistically significant improvement. Okay, finally, we have to thank many people. We have to thank Track for providing the data. We have to thank BBN for providing named entity taggings for us. IBM did the feature extraction prior to the workshop, and Arno Arme did the closed captioning alignment. Then we had help with GMPK. During the workshop, there was email correspondence with Jeff, and even during this presentation, we'll get still software support. And during the workshop, Karen Devesco helped us quite a lot with GMPK on site on the keyboard.
She was our GMTK psychiatrist.
We got the capitalizer from last year's machine translation team. INRIA provided the face detector, and then all that is not possible without money, so we'd like to thank NSF, Darker, and NSA for providing the funding. And finally, CLSP for hosting the whole event, in particular Laura, Sue, and Chris, who are unfortunately not here right now, for doing all the administrative and organizational matters. Then we would like to thank Ivy, John, and Peter for keeping the computers up all the time. So we had just to do the research, and finally would like to thank you, Fred, for making the whole event possible. Thank you very much.
Keep it on.
Okay.
If you're done. So we now have a discussion. You're done,
yes,
right?
You're done. If you're now in the discussion
We're now
section.
in the discussion, right? So I don't want to forget something. Here, this line here. I got email from Charles Wayne, who is this. and he is wondering if he should support us again next year. And for that, he needs to have highlights. And so I wrote back that highlights will be provided tomorrow. No, this is serious. This is very serious stuff. So I expect you, you and I guess Dan, you, because I don't see. I think Richard went home or something. Right? Right. So I expect you guys to provide me with highlights tonight.
Okay.
And I will write the email tomorrow. Okay, so that's number one. And number two, of course, there will be an opportunity for you people to thank them at dinner time, and I would appreciate if you would. So, thank you, and so now there is general discussion.
So, yes, we are now in that section, and yeah, I think Andreas was first.
So I mean, it took me until the last slide to realize it, or one of your last slides to realize but so your concepts are really like the phoneme set of your problem.
Kind of, yes.
Yes.
So that was more common.
Except for the fact that a lot of them are ignored. I mean,
Well, there are similarities.
oh yeah, a lot more are being ignored.
Yeah.
A lot more being ignored.
It's a very small subset of the potential visual phoneme vocabulary that we do test.
Yeah. Michael?
So if I were to summarize this in one sentence, the audio-visual fusion is giving you 14% improvement in query retrieval. Is that correct?
In the information
Now,
retrieval.
I know that we've done a fair amount of work, at least at the concept level at IBM, on doing audio-visual fusion. And I'm just wondering whether, if you can jog my memory, and also I think everybody else would be interested as well, as to comment on how well what went on here, how that compares to your previous work in the area.
Sure, yeah, I can answer that. So in the concept detection task, we have looked at fusion, in particular for this concept detection task, we looked at a variety of fusion models back at IBM. In particular, we also explored some SVM detection mechanism. There, if you relate that to this particular matrix, it's like doing P of C given DW, right? So we're looking at the whole information together in one set and then doing some analysis. There, the fusion models have typically given us a lot more gain, on the order of about 30% to 40% on the concepts, in detecting the concepts. We haven't managed to demonstrate, this is the first time we are doing automatic annotation. Even at IBM, the only things that we tried were manual retrieval tasks. Going back to the list diagram, we were doing the manual retrieval task, and there when we did the fusion, sort of positing what could be the possible query weights and stuff like that, we were getting about 20% improvement last year. So this was quite encouraging that with purely automatic techniques, we were getting 14% improvement. So it was quite that we could get that close. And
so what you're saying is when it comes to concept retrieval, that our visual only techniques are giving 12, 14, 15% mean average precision.
Yeah.
The text only techniques gave us 12% mean average precision.
You get about 40%. Yeah.
And there is an experiment out there which says that if you put them together just for concept retrieval,
yes.
you can expect to get about 30% or so.
Yes.
So that would work here if these pieces of information are totally complementary,
correct, yeah.
which they're likely. Well, I
Yeah.
guess
They were likely to yeah.
I think there was some question back there.
So can you go back to your first model in the talk you just did? If I were going to try to build this, I'm not sure I would look for a lambda that was insensitive to length, because the value of the words probably increases with length, whereas the value of the image is probably less sensitive to length. So the relative value of the image would seem to be greater if the shot was longer, because, I'm sorry, the relative value of the words would be greater if the shot was longer because there'd be more words. Is that something you thought about, tried, other people have tried? It seems like if there are no words, it can't be of much value.
Yeah, you should remember that there's a NIST video retrieval task, so the queries have been designed very carefully to have a visual component. For example, they say things like, look for images of the Yasser Arafat. I want images of Tomb of the Unknown Soldiers. So they have purposely chosen those queries to make the images more relevant, just to make sure that the distinction between that and the SDR task is quite clear. And I would probably, the lambdas are definitely dependent, and I would take it further and say the lambdas are query dependent. They are not dependent on just the number of words, but are dependent on the particular, for different queries we'll have a different lambda set.
And that may be true, but I don't know how to model that when I know how to model the number of
Yeah,
words.
that's a crucial issue.
That's a
So
very
we
crucial problem.
did some kind of experiment, kind of what would be the ideal lambdas per query, but we don't have any
But it's
way
not-
to.
But the question isn't per query, the question is per document.
Yes.
The documents, your documents, if I understood correctly, sometimes have no words in them.
But they fit this terms, yes. Okay, but that's an issue, yes.
Okay. The second question that I have, which is a broader question, is I think if I were to try to give a one-sentence version of this, I'd say that pre-annotated concepts that you can use as training data, you've demonstrated are a useful crosswalk between the words that appear in queries and the images that you can process. But where do you see this sort of data occurring in nature that you could take advantage of? Or where is the business process that builds this data affordably? Or is there some third way that now that you can do this, you had something about direct modeling, can you avoid the need for this kind of annotated data? So how can I think about actually getting out of the research realm here and solving a problem that my mother would care about?
My
personal rephrase it. Are you saying that how are you going to do this experiment if you don't have the training data to begin with?
Or how are you going to get the training data?
Well,
I mean, not as an abstract problem, but as I want to actually think about how, I can see how I'd use Google, right?
So in some sense, you can potentially do experiments like that. Training data is an expensive problem. You have to get a whole bunch of annotations, and it's very similar. In fact, it's more compounded by the fact that there are a lot more things in an image to annotate compared to standard speech recognition scenarios. So yeah, that is true. It's a much more expensive proposition. In fact, we did when we were doing these annotations for Trek, we found that there's a factor somewhere between 8. It's a 8 times real time factor. That's what is the annotation cost. And we have some tools to try to speed that up to bring that number down.
It's just 8 times real time, because that's not that far off from the speech transcription anyway. And we're certainly annotating billions of.
Yeah, everybody doesn't annotate the entire level of what is there in the image. Right? Some people mark only 3 things, some people mark 14 things in the image.
I'm just saying 8 times real time is not out of range with what we do in transcription these days.
Yeah. The problem is one of vocabulary, right? I mean, so if you don't annotate a blade of grass, I can't find a blade of grass.
The question is,
For this fixed vocabulary, there's maybe an answer to Doug's question, which is to use code training, since you have, since you find that both the ASR and the image are independently useful in identifying the concepts, you may be able to ping-pong those off each
in
other.
fact,
But that doesn't get to Doug's real question, which is how do you get beyond these 75 terms?
Right now the only way we know is either we need a lot more data. We need some simple direct modeling experiment, and that hasn't helped us much. In fact, that goes way lower than any of the concept detection experiments that we did in terms of performance. So we do need these concepts, that much we know. And how do we get beyond that bottleneck in terms of the data? It's not clear. We know right now that we need the data, but how are we going to get it? How it's going to be solved?
There are some sources of data, they're not publicly available, like Corpus, they're annotating millions of images.
Yeah, so has CNN. They have
related, I'm wondering if you're familiar with this work, which is popularly called the ESP game. It came out of
Jason's first question at the beginning of the workshop. Can you use the taboo? In fact, that's a very valuable source of data. Like barring the modulo, the interlabeler problem, which they have solved in a very interesting way, yes, that's a very good source of information. There are some issues that one need to look at in terms of the fact that these images are fairly unconstrained. So there are some image processing challenges that we need to overcome. But other than that, that's a very good data set to look at. So Doug, if you're not familiar with that particular thing, what Jason and Arnaud were suggesting were, there's a game that's out there on the web. We're given a picture, two people annotate independently, and the system allows the annotations only when both of them match. And people have collected a large...
That's likely to have even more annotation problems than...
There are some challenges, but
I've seen people playing that game, and sometimes people get frustrated and they just try random words, and sometimes the random words match.
It's a hard problem.
That's unlikely.
Because
So
it's
a
time
little
constraint.
No, so what we need is we need to modify that game. Then every now and then you sneak in an image for which you actually know the ground truth. And if one of these spurious matches happen, you take off a lot of points from them. So that way they'll be dissuaded from trying.
Any other questions?
Well,
So
I was just, I mean, I don't know whether this is doable. I was just thinking what was said now. Couldn't one go edit so that one would sort of intersect the various images and find out what's common to them? And I'm talking about the leaves of grass, for instance. And eventually one would get down to pictures of leaves of grass, and then you would only need to ask someone to name it. And once it was named, then it would be spread out to the various images which had it.
Yeah, people have tried.
And that would not be that computationally
You have to start with
intensive.
similarity somewhere, right? You have to say that the similarity is based on color or some low level property.
Well, you people, image people, have to solve. But I'm discussing the fact that if you solve it, you can.
That's the hard problem to solve.
Pardon me?
That's the hard problem to solve.
It sounds like you would almost need a full object recognition system to do that. And vision has found that to be very difficult.
And you couldn't do it through features, and that if something has...
No, that's much harder to solve than what we are trying to do. So,
And so you have
for retrieval, you only need to say, okay, I can get in the top few pages, I can get good images. In object recognition, you're trying to label every image accurately, and that's much harder to do.
No, I'm not thinking of... I mean, there may be some sections of the image which you can say similar to some other section of some other image.
For something, grass sky, for the easy ones.
Well, in some special cases, like face recognition,
Yes,
right? So if you pair the caption OCR with face recognition, which is a highly developed technology, right? You could conceivably automatically build a database of images, right?
Yeah, there was
that's what I think.
Yeah, but there are only a few things like which you can do well.
But this happens to be a very relevant one.
Yeah, I think people already do.
Okay.
Well, what do the Dutch know? No, what do you suspect, in other words, that they have used which was not at your... I mean, there must be a paper, right?
No,
there must be an article which explains this out.
How would you answer it? Because,
It's nothing special. They've been working on it for a while. They're very careful. That's the main.
No, the other thing is that the block that we did not touch was the one where you look at the similarity of the test images to the images you're returning.
Yes.
And this is a direct image-to-image comparison. And from what I understand from our group discussion, they use that. And perhaps that's very valuable, and we didn't spend much time on it, so we didn't.
Because you didn't.
Because
you ran out of time.
Yeah, no, we
Yeah,
chose
it was also from the very beginning. I mean, those are the two contributions where we match words with pictures.
Yes.
We weren't really worried about matching words. That was from the very beginning clear that it's outside the scope.
that was something that we had sort of left out for the workshop. We were interested in it, but we hadn't done
What
it.
they were doing was, as part of the query, you also have some images. And they were directly matching the images from the query with the images in the database.
Okay. Anything else?
So, was one question back there, I think.
Oh, I had a dumb question for image processing people. So there's this, people use CRS to generate these textures, right? And so you can essentially generate a texture for the skin of a tiger. And can that be used the other way around to detect? Like with the same kind of idea that HMMs are used for recognition and they can be used for generation, but they do a really sloppy job of generation. And so,
You mean turn the HMM the other way around?
so you can. So the concept is that you can use the HMM for speed generation also, even though it does a very sloppy job of it. With a similar concept, I'm saying like there's this automatic generation of textures, right? I mean, people have worked on it. Like you say that I want to fill this, like this surface with grass texture, say. So there are automated tools which will do that for you. Can those tools, like those things, can be used the other way around to detect that this portion is grass?
So you're suggesting something like looking at graphics synthesis tools and then saying comparing that with
Obviously you can't use those tools as a black box. I mean, understanding the
but essentially saying
people are
HMM is generating
textures.
outputs. HMM is generating outputs which can be modeled and which
I'm
are
under the
those
impression they
things.
use like CRFs to do these things. So there is some statistical concept which is going into generating these textures. Right? Can that concept be turned the other way around and be used for detecting the textures?
So saying that if this texture is present, I thought that was what the HMM models were.
No, but let me take a crack at interpreting your question. So the analogy in speech would be there are these very good speech recognition systems. So if my recognizer thinks it has recognized this sequence, this two-word sequence over here, can I somehow use a good synthesis system for that sequence of words in my model? And one possibility would be if you had a direct metric on similarity of the acoustic waveforms, perhaps you could measure the similarity between that segment of the waveform which your recognizer thinks is Bengal tiger, and try to see how it sounds how it looks compared to what a synthesizer would produce for Bengal tiger. But short of that, I don't know any technique of putting that into this model, because the two problems are significantly different, right? When you do synthesis, you want one good realization of Bengal tiger, whereas there are millions of sloppy pronunciations of Bengal tiger like we heard yesterday. And the same thing holds in the visual domain, that all sorts of strange things are tigers depending on how they're illuminated, how the shadow of the tree falls on them, and so on. And calling all of them tiger is what this model is being asked to do. And you have a good point. I don't know how to use it. If the models that were used for texture synthesis could assign likelihood, then of course there's a direct way of using it in this setting. But I believe that the best models don't
Probably
assign
they
likelihood.
don't, but conceptually probably they can be extended to.
Okay, Mary had the last question, and then we'll close.
So one of the things that I think I haven't seen here is better use of the structuring of the broadcast news stories. In particular, there is a lot of information in terms of typical types of story structures and the likelihood that someone's name is going to co-occur. So there's a lot of introductory phases in terms of introducing the next segment. And yet there are going to be other cases where, and it's not completely covered in that, I think. There's just these recurrent story structures that I think would have an impact.
Yeah, that's definitely
And
valid.
it does seem to me that in terms of making the visual models and the speech models more coherent, that's an important bridge.
But it's also kind of, we're 10 people for 6 weeks.
No. It does seem to me, if I were going to pick the thing that might have the biggest impact, that would be what I would go with.
Yeah, it's definitely a good suggestion for the future work. But I also think that...
And I do think they are very generic.
Yeah.
Well, you can put it into a proposal for next year. We are soliciting those, of course.
Yes. You had a response to that? No, for the question.
She's just not.
Yeah, actually, I tried that thing and it is working better than just using all the shots only. I just extracted commercials, some anchor things and so on, and then I did story segmentation, and then I removed anchors, commercials, and so on, and then again, classifiers associated with the side, and it is giving better results, but still not complete. So it's a very
It's
good
a
future work.
It's working, it's
Yeah.
work in
I'd
progress.
suggest that we just close the discussion here and that whenever there's something else to discuss, I mean, we can go out to lunch, dinner, whatever, and continue the discussion.
Okay, well, thank you very much for all those presentations. We will see you at dinner, and hopefully you know where to go, etc. There are going to be drinks and so on and so forth. I've already mentioned that we are soliciting proposals. As you see, we are branching out to visual things. This is not the first time we had visual. I don't know what year we had Chalapathia, but
99, I think. Was it 2000?
2000. But you know, we are willing to branch out into other domains as well, from language and speech. I guess the important thing is that to us, in some sense, is that it be well, I should say that it be grandfathered by speech recognition, because all this stuff is grandfathered by speech recognition, by the approaches that were developed in that field, and they are now spreading. And presumably they could spread elsewhere, and we'd be interested in having it at the next workshop or the workshop after. Well, so thank you very much.